Dear students, on the last lecture we have discussed F19 NMR spectroscopy. Today we are going to discuss with the phosphorus 13 NMR spectroscopy. Phosphorus 13 nucleus has a natural abundance of 100% and the spin quantum number is half. For phosphorus hydrogen coupling, multiplicity rules are same as for CH-CH. Coupling constants are large. JPH is around 200 to 700 Hz and JCPH is 0.5 to 20 Hz and are observable through at least 4 bonds. There are no rules for the prediction of C13 chemical shift and the range is fairly large. Consider the spectra of the compounds such as triphenyl phosphorus, phosphoric acid H3PO4, diethoxy-POCl, phosphorus oxychloride has phosphorus atom differ widely with respect to the valence state. The group attached to it, yet every compound has the distinct chemical shift and provide useful information even in the absence of predictive rules. In Wittig reaction, an aldehyde or the ketone is treated with the phosphorane, a phosphorus halide, to produce an olefin. The phosphorus 13 NMR spectra shows that oxaphosphettanes are the intermediate instead of betanes, since the spectra of the reaction mixture at the low temperature are in agreement with the oxaphosphettane and not with the tetra-coordinated phosphorus species, as is the case with the betanes, the phosphorus halide and the phosphine oxide. The proton decoupled phosphorus 13 spectra of triphenylphosphine PH3P give a singlet. In human muscles tissue, the phosphokeratin is converted into keratin and phosphate during the exercise with the release of energy. Phosphorus 31 NMR spectra can follow these changes. You can see phosphorus 13 NMR spectra of phosphokeratin before the exercise. ATP molecule will be converted into ADP molecule, and again after the exercise we are having the second spectra, that is the phosphate after the exercise, and you will have the phosphokeratin. After the exercise, C13 absorption of phosphokeratin in the forearm of man begins to decrease and the signal due to the C13 of inorganic phosphate begins to increase. The 3 alpha, beta, gamma phosphorus 31 atom of ATP which are not involved have their display themselves at the appropriate chemical shift in both these spectra. In case of nitrogen 14 spectra, the electric quadrupole can effectively provide the vector necessary for the excited proton to relax. Evidently, the splitting of nitrogen nucleus by a proton is not resolved. Double resonance technique can be used to remove the broadening of absorption. Now, next topic is the NMR spectra of carbocations. Certain carbocations are sufficiently stable under the definition condition and their PMR can be easily studied. For example, alkyl fluorides in liquid SO2 reacts with the antimony pentafluoride Lewis acid to form a solution of carbocation. Let us consider the formation of carbocation from the tertiary butyl fluoride with the SbF5. So you are having the doublet at the tau 8.65 for trimethyl fluoromethane, and SbF5 in the liquid sulfur gives the CS3 whole thrice C plus SbF6 negative singlet tau at 5.65. In carbocation, central carbon is sp2 hybridized, hence de-shielding causes the absorption at low field. The position of absorption in case of isopropyl fluoride are as shown below, that is the CS3 to CHF. You will have a quadrate. CS3 is having the 3 proton and adjacent carbon atom having the 1 proton. So you will have the 1 proton will couple with the 3 proton giving the quartet at tau 8.77 and SbF5 a multiplate at tau 5.35 giving you CS3 whole 2 CHSbF6 negative. So a doublet at 4.95, CS3 is coupling with CH and CH is coupling with the 6 hydrogen of 2 methyl groups, giving the septate delta 3.50. The signal due to the positively charged carbonium ion shows the enough downfield shift. So this is about that if the fluoro compounds, which is the electronegative atom in the periodic table, so you will have a downfield shift if it is attached to the fluorine, and fluorine can also couple with the proton on the adjacent carbon atom. So thank you very much.